Hi Geometry, this is page 583, Unit 5, Lesson 10. So this first picture is a stack of quarters. And if you look at stack A, this is what we would say is straight up and down. In geometry, we call this right, meaning that the sides are straight up and down, perpendicular to the table that they're setting on. In B, you would say that this stack of quarters is slanted. Someone took their fingers and gently pressed all the quarters over the side, so they're not going to fall over, but it's slanted. In geometry, we call this oblique. So let's talk about the volume of this stack of quarters. So in this stack, we've labeled them how they are different from each other, and they resemble cylinders, and we know how to find the volume of a cylinder. The volume of a cylinder is the area of the total base times the height, and in a cylinder, the base is a circle. So we generally write the volume formula to be the area of a circle, pi r squared, times then the height of my cylinder. So how do these heights compare? Well, this is the important concept from today's lesson. The height of this stack, it's really hard to count. I tried a couple times. I think there might be 16 quarters in this stack. So let's for a moment just say there are exactly 16 quarters. Then the height of this stack is 16 quarters tall. When I push it over, I haven't actually made it shorter. The actual height of this stack is still the same 16 quarters tall. The stack itself is just slanted, but as far as the actual height, then it would still have the same height. So my volume is the same circular base area on both sides. There's the same quarter at the bottom times the exact same height. So since they have the same base area and they have the same height, these two cylinders, one being a right cylinder, one being oblique, would have the exact same volume. So it doesn't matter that my solid is slanted. If we take a look at the next page, the next diagram is trying to get us to understand the same thing. It says this image shows two rectangular prisms. The bases are congruent. So inside here you can see this orange rectangular base and this rectangular base. Remember, the blue rectangular prism is a stack of this base from the top to the bottom. And the green one is also a stack of this exact same base, except if you could imagine a deck of cards, every time you stack up the next rectangle, it's slightly askew, which means by the time you get to the top of the stack, it's slanted. But it's the same number of cards in your deck of cards, and it's the same area of each cross section. And so since each base has the same area, and since each have the same height, then we're going to find that they have the same volume. Step 3 down here, remember my volume is my base area times my height. So going back up to number 1, it says sketch the two cross sections. Well, those are my two congruent rectangles that you can see in the diagram. How would the shape or area of the cross sections change when we move them up and down? Well, they don't. They would be the same. In my blue stack, I'm just stacking them straight up and down. I'm stacking them right on top of each other. However, in my green one, in my green stack, I am stacking each rectangle slightly askew. Not really sure if askew is a real word or not, but in my mind, I can see my rectangles simply being stacked slightly askew of each other, creating this stack of rectangles that is slanted, if you will. This height of this stack, if I have the same number of rectangles, is exactly the same as stacking that exact same rectangle perfectly on top of each other, and I get the exact same height of my stack of rectangles. So that means that my rectangles would have the exact I'm sorry, my three-dimensional rectangular prisms would have the exact same volume, exact same base area, exact same height, exact same volume. So let's take a look at some of these diagrams. These are not necessarily oblique pictures. In this activity, we're supposed to be pulling together what does it mean to have equal volume. In other words, what is my base area times my height? Would that value be equal? So let's take a look at several of these in this video, and the others we'll take a look at in class on Zoom. So in my first diagram, on the left side, I have a cylinder. And in my cylinder, my base area of my blue circle is done for me. It's 12. And the height of my cylinder is 6. So for my cylinder in number 1, my volume would be my base area times my height, or in this case, 72 inches squared, units squared, cubed. Units cubed. It depends on what my dimensions are measured in. So let's take a look at my second rectangular prism. Again, remember the volume is the base area times the height. The base area in this case is a rectangle, and it's 4 by 3. So my volume of my rectangular prism that you see here is going to be my base area 4 times 3 times my height of my prism, which is 6. So this is 12 times 6, or again, 17 units cubed. You can see since they had the same base area, since their big B's are both 12 and their heights are both 6, that these two three-dimensional figures have the exact same volume. So let's take a look at number 2. Number 2 does bring in this new vocabulary word of my oblique cylinder versus my right cylinder. So in my oblique cylinder, I notice that my base is a circle with a radius of 3, circle with a radius of 3. So really my base areas would be the same. If I think about my volume formula is base area times height. So we'll do my base area times height for both of these. In the oblique cylinder, my base area is pi r squared, in this case pi times 3 squared. You can imagine that's exactly the same thing as in my right cylinder. It's also a circle with a radius of 3, so it would be pi times 3 squared. Now let's talk about what my heights are. Remember, the height is the perpendicular distance between the top base and the bottom base. The actual height of my oblique prism is 7. However, the height of my right prism is 10. I want to introduce to you the idea of slant height. This 10 right here, written on this side right here, that's called slant height. The slant height of my oblique prism, or my oblique cylinder, is 10. My slant height has a use. I use it for surface area, but it has nothing to do with volume. So that 10 really right now is just a distractor in this picture. The 7 is my height of my oblique prism. My oblique prism is shorter than my right, I keep saying prism, My height of my oblique cylinder is 7. My height of my right cylinder is 10. So this would have a greater volume if I took the time to calculate it, greater volume. And this would have a lesser volume than the other one because my heights are not equal. Let's take a look at the next number 3, which also has an oblique cone and a right cone. I know it's a right cone. I can see the right angle right there. And I know this is an oblique cone because it's slanted. However, notice, just like in the last problem, my bases are circles with a radius of 3. So when I look at my volume formula, base area times height, this base area, by the way, for a cone, it's going to be 1/3. We actually haven't used that yet, so I'm going to, it's 1/3 my base area times my height. We haven't actually learned that yet, so I'm just kind of sticking that in there. Anyways, my base area is a circle with a radius of 3. So my base areas are the same. However, if you look at the heights, my actual height from the top of my oblique cone to where my base is setting is 5. The height of my right cone from the top of it to where my base is also 5. So this one will have the same volume because my base areas are the same and my heights are the same and the formula for the volume is the same. And so these would have the same volume, unlike number 3. We'll talk about 4, 5, and 6 in class. So if I could go to the next page, if I could go one more page to the homework, I want to talk about number 3. Number 3 was confusing for students before, so I want to discuss it. So there's 2 problems here. Problem A is the volume of this crystal vase if the glass has no thickness. Problem B is different. It is the volume of this crystal base if the glass is a 1/2 inch thick on each side. So that will change my math. So let's read this problem. This is a zigzag crystal vase that has a height of 10 inches. So from the base sitting on the table to the top of it is 10. It doesn't matter that it's zigzag or not. The cross-sectional area, the cross sections parallel to the base are always rectangles that are 6 by 3. So if you could imagine, this is a stack of rectangles that are 6 by 3. So it doesn't really matter that they're zigzag versus just stacked perfectly on top of each other. It's the same base area, the same rectangle on the base, and the same height of 10. So volume equals the area of big B times H, or in this case, since it's a rectangle, it's 3 by 6 times the height of 10, which in this case would give me what, 180? And is this inches? Sorry, I'm writing into the gray area. I hope you can see that. Inches cubed. So how does this change if my glass has a thickness? Well, if you can imagine, your volume is if you fill this with water, it's the amount of water that goes inside. So now if your glass has a thickness, your base area is really not 3 by 6. If you can imagine, if I look at my base, this is a vision of my base that was 6 by 3. If I give my glass some thickness on all sides, then when I pour my water in, I'm not really filling a base area that's 3 by 6. My base area, if I take a 1/2 inch off on either side and a 1/2 inch off on either side, then I'm taking 1 inch off. It's really 5 by 2. If you can imagine, this is half, this is a half. So I'm taking a whole inch off the length and getting only 5 inches. If this is a 1/2 inch and a 1/2 inch, I'm taking an entire inch off this width of 3, and so it's really only 2. As I'm looking, my vase, if you will, up at the top, my vase, and this is my base at the bottom, and it's zigzagged up to the top. So I'm not really concerned with the zigzag part right now. But if you can imagine, the top has no thickness because it's open to pour in my water. However, down here on the bottom, the base does have a 1/2 inch thickness. So instead of being 10 inches tall, now that I'm using up a 1/2 inch for glass at the bottom, it's really 9.5 inches tall. I don't need a 1/2 inch at the top because my top of my vase is open to pour the water in. So my actual dimensions, if my glass has a thickness, the area of my big B is now 5 times 2 instead of 6 times 3. And my height is really 9.5 instead of 10 because my bottom has a 1/2 inch of thickness of glass. So the actual amount of water going into this is 10 times 9.5, or 95 inches cubed would be the amount of water I'm pouring in. Thank you very much.